Okay, we're recording. Real quick before we get into the math, I just want to remind everybody, don't forget we have a test on Friday. Good luck to everybody in studying for that. Also, while we're on the topic, I'll remind you further, what we're doing today is not fair game for the exam. Right? So if you look at the lecture schedule, the color coding indicates which lectures worth of material are fair game for the exam, and per that color coding, we are currently doing exam 3 material today. So none of this is relevant to the exam coming up. But of course, the third exam is not that far away, so we got to start working toward that as well. Okay, so we believe we were talking last time about this idea of center of mass. And I think a great way to think about it is it's the weighted average of position. So you notice both in this first example of a formula we wrote down and in this eventual sort of generalization that we wrote down, it's literally, we're taking a position, right, is what we're doing an average of, a weighted average of, and the weights are literally the masses. Right? So we talked through the details of that last time, and what I want to do now, and I made the observation that you can compute this one coordinate at a time, which is convenient, I think also intuitively satisfying, but it's also true and very convenient. And so here we go. We're going to do an example here. We're going to compute the center of mass of this upper half disk like that, this thing here, with the understanding that the density in there is constant at 1. So just to keep things convenient for this first example. Okay, well, we have explicit formulas, and again, for the x coordinate, here you go, weighted average of position. Specifically, the x coordinate of the center of mass is the weighted average of all the x coordinates. And you'll recognize that this formula here is literally a weighted average. The complaint one might make is, hey, what happened to the density? Well, this density in here would have been down here in this denominator. After all, mass is density times area. But it also would have been up here in the numerator. After all, mass is density times area, and that constant factor of density would just cancel. Okay. And of course, it's also just 1. So either way you like it. Okay, so we indeed have then, this is a weighted average of position, and this integral, I'm going to leave the details again to y'all to check. This is a good exercise to check through the details, but remember there's 5 conditions you have to check if you want to make a symmetry argument, but this integral is susceptible to a symmetry argument. So think that through. What is the line over which I'm making my symmetry argument? How do you do reflections? How do I know that integrand is odd? Blah, blah, blah. Right? Fill in those details. This integral is 0 by symmetry. Okay. Now, I do want to comment one thing here. I've seen different arguments get made as to why this should equal to 0. Here's the different argument that I've seen. This is what I call a physics argument, which this isn't a physics class, so I don't think this is appropriate for a math test, right? But the physics argument is to say, oh, well, look, if I were to draw a line right there and imagine that this mass is balanced on that, or trying to balance on that line, well, the torque on the left and the torque on the right are exactly the same. They're just equal and opposite torques, and so it should balance. And doesn't that mean immediately that the center of mass is on this line? And doesn't that immediately tell us that x bar is equal to 0? And, well, I suppose, but that again is a physics argument. And in this class I'm looking for math arguments, not physics arguments. So please don't give me the physics argument. Please do give me the math argument. Specifically, give me the 5 steps. And if you were to make such a case, an example like this. Is that clear to everybody? Okay. All right, let's look at the y-coordinate of the center of mass. Y-coordinate, here you go, weighted average of the y-coordinates. All right. You can slice this up either dx dy or dy dx. Take your pick, doesn't matter. in terms of the answer you get anyway. Either way, you're going to get the same final answer, so suit yourself. Let's talk for a minute, though, about which one should suit you better. I think there's a pretty clear preference between these two options as to which one is the uglier integral. And this is an example of an aspect of integrals you might not have thought through, so I just want to show you how this plays out in this case. The temptation is to look at this and say, ooh, check it out. Y is further to the outside. That means that Y is a constant for the purposes of that dx integral. I love it when my integrand is a constant. Life is good. Let's go that way. And you could do that. But I like this argument. If you look at this right here, y dy, it's not that hard to integrate. You get y squared, well, 1/2. But the point is you get a y squared in your antiderivative. That square cancels with this square root, and the square root goes away. That, I think, is the bigger win, right? So I strongly encourage you to think of, try to think through not just what's going to be the easiest first step, but what's going to be the easiest later on down the road. And opportunities like this where you have a square root and the opportunity to create a square, this is a good thing. Okay. Next idea. Moment of inertia. This is another physics idea, and I emphasize this is not a physics class. So why do we keep doing physics if this is not a physics class? And a couple of answers. On the one hand, I do want to be able to give you examples, right? I mean, a lot of the real world engineering relevant, I know a lot of y'all are engineers, examples of how we use calculus tend to be physicsy very often, right? Not always, but very often. The other thing is sometimes physics gives questions that give great opportunities for how to use, how to motivate some mathematical ideas. So anyway, I'm going to try to keep this as much as possible about math, because this is a math class. But the physics is going to be in here, but it's going to be in here for the purpose of serving math. Okay. All right. So here we go. If you have a circle, I hope you all remember this high school geometry formula. Arc length is radius times angle. Basic geometry formula. And if you think of distance as a way of keeping track of sort of, in some sense, where you are on that circle, then I can take a time derivative of both sides of the equation. Radius is constant, of course. You take that time derivative. What that tells you is that the rate of change of your position, aka your speed, is r times, well, the rate of change of your angle. Now, let me make this observation. The angle is another way of keeping track of where you are on the circle. You can think of that theta as being a coordinate of sorts. Even if we haven't, created a coordinate system and named it, we could think of that as being a kind of a coordinate. So when you take the derivative of a coordinate, that too should be and can be, it often is, and I like the fact that it is thought of as a speed. But keeping in mind, this is not a rate of change of distance, so we're not going to call it speed or linear speed. This is a rate of change of an angle coordinate. And so we call it angular speed. Very, very common idea in physics. It's a big deal. Very useful in a lot of physics and engineering. Whenever I say physics, by the way, I mean physics and engineering. Okay. So angular speed. By the way, sometimes this gets sloppily referred to as angular velocity. I might even say it myself here or there. Apologies in advance. It's not really quite the right concept, but close enough for what we're doing. Okay. So big question then. Suppose I have some big blob of mass like this, that's rotating around this axis, right? And as it rotates around, it's got, it's moving, and when mass moves, there's kinetic energy. Reasonable question to ask, what is the kinetic energy of this rotating mass? And here's the problem. It's very tempting to say, 1/2 mv squared. We all memorized this formula back in high school physics. Side note, if you haven't had high school physics, don't worry about it. This is the formula for what we call linear kinetic energy. If you have a mass moving in a straight line, Boom, there's your formula for kinetic energy. Kinetic energy is, you can think of it as how much work does it take to create the motion that you're describing. It's just a fundamental physics concept, but that you don't need to understand it in depth. But can we use this formula? And I say, tragically, no, we can't, because look at this. If I were to look at this little piece of mass here, that little piece of mass, in the time it takes for our blob to make one revolution, moves that far. But if I look at this little piece of mass over here, it moves a much greater distance in that same amount of time. That little red piece of mass is literally moving faster. It has a greater speed than the blue piece of mass. So if I wanted to use this formula right here, 1/2 mv squared for kinetic energy, which speed would I use? There is no speed to use. There is no shared speed. It's a different speed for each particle in this lump. So, can't use this formula. So, here's what I consider to be the good part of this discussion, and that is I don't have to use this formula. I can break up the question into little pieces, and I need to get rid of let me redraw my lump here. Alrighty, so there's my lump. I'm going to take that entire lump, I'm going to break it up into little pieces, like, for example, this. Right there's a little bitty piece of mass. And I argue that however much kinetic energy that little piece has, if I were to then add up over all of those little pieces, chop it up, add it up, whole's the sum of the parts, the total kinetic energy is the sum of all those little bitty pieces of kinetic energy. And that is what I would get. That's what I argue right here. The total kinetic energy is the sum of all those little pieces of kinetic energy on these little pieces that I get when I chop it up. This is a Riemann sum argument. Everybody buy it? Okay. Good news. On each little piece, there's a well-defined speed. On that little piece, then, 1/2 mv squared, no problem. The speed on this little piece, perfectly well defined. That little piece is small enough. All the mass is going the same speed. Again, close enough, round off errors go away in the limit, etc. Okay, cool. And then I further can argue that speed we've already calculated, right? It's r omega. And as this thing rotates, I make the case as it rotates that even though different pieces of my lump are going different linear speeds, they do all have the same angular speed. And the amount of time that any part of this makes a full loop, the whole mass makes a full loop. It's the same number of, degrees per second or, radians per hour or whatever. The angular speed is a constant, yes. In this formula right here, 1/2 v squared, and the m is this dm right here that represents the mass in that little piece that's actually moving. Yeah. Is that cool? Yeah. All right. So omega is constant. That means that this omega squared I can factor outside of the integral, like so. And now we're to the point where we can do some sort of creative interpreting. If you look at this equation, which you'll see I've rewritten like so, this seems like a cheap trick, because after all I did there was take this odd expression and just rewrite it as I. I'll come back and explain my motivation for that in a minute. Looking at this expression then, look at this wonderful seeming coincidence. What I have down here now is a formula for kinetic energy that looks a lot like my old formula for kinetic energy. It's just that this is angular friendly. Instead of linear speed, here I have angular speed. So instead of linear speed, I have the angular analog of speed down here. So with that as a pattern, if you will, I'm going to say that mass, the angular analog of mass, is what this I thing is. So the reason that I want to take, the reason I want to take this expression here and give it a name, I'm going to label it as I. I'm going to call it a name for future reference. I'm going to call it moment of inertia. Is because in this equation, it's the angular analog of mass. When you're describing kinetic energy, but you want to talk in an angular sense instead of a linear sense, that thing plays the role of mass. So anyway, this is a nice little physics perspective. It's extremely useful. For example, in engineering, my favorite example is if you suppose you're engineering cars. Right? And, fuel economy and all that, right? That's a big deal. Really big deal. Every little microscopic little bit of fuel economy is extremely valuable. Well, fuel economy is about energy. Some of the energy in a car driving down the road, we tend to think of the energy as, well, there's a big heavy car and it's driving in a straight line. But there's another form of energy, and that is the rotational energy of the wheels, right? So it's not good enough just to know what the mass of your car is. You also need to know how much kinetic energy is there in the rotation of the wheels. And that's computed by this formula, which very importantly depends on this thing called moment of inertia. So if you're designing car wheels, you need to understand moment of inertia and how, pros and cons of, it being larger or smaller, and there's a very complicated discussion that ensues. But it's a very, very important concept in engineering. Okay. All right. So, one little bit of bad news. You see this R here, and we've used R previously as a coordinate, as a cylindrical coordinate. Here it's not, and this is really, it's kind of a confusion of variables here. I'm not happy about the state of affairs of this, but there's nothing we can do about it. This R is that distance. It's or let's say this distance here, equivalently. It's the distance from your axis of rotation. If I can there we go. It's the distance from the axis of rotation to an arbitrary piece of mass where we're, computing kinetic energy or what have you. So R is the generic formula to my axis of rotation. It's not necessarily the cylindrical R. So what you've got to do, tragically, is look at this every time you have a moment of inertia question. Look at it as I've got to identify what my axis is, whatever it might be, and think in terms of, depending on where that axis is, what is the formula for distance? Well, there, the formula is that. Here, different line. Totally different formula for distance to that line. Here, totally different formula for distance to the line. Likewise here, totally different formula. It's a different little geometry problem every time. So, again, heads up. Now, sometimes you get lucky. Like in this case here, it happened to be, because we were going around the z-axis, that R, conveniently, is the cylindrical R. That was a lucky break. Most of the time it won't be. So apologies for that. That's nothing I can do about the conventions, and unfortunately using R in this circumstance is pretty standard. So the way we have to deal with the confusion of variables is y'all just have to be heads up about it, and just make sure not to accidentally conflate the R as we're using it here with R from cylindrical coordinates. Let's see an example. Let's get our hands dirty. So we have here this solid. Right? And mass is distributed throughout that solid per this formula here. This is saying how much mass is where. Mass per unit area, of course. And what I want to do is imagine that that's rotating around the x-axis. Or, correction, I want to imagine that this might someday be rotating around that x. It doesn't actually have to be moving at all. But were it to be moving around the x-axis, what would be the moment of inertia? What is its moment of inertia around the x-axis? Okay, well, the way we do that, this formula, integral r squared dm. Here's some good news. It's always the same formula. It's always integral r squared dm. Notice I've got a two-dimensional example here, so it's a double integral. Previously, I had done a three-dimensional example up here, and so here we had a triple integral, but it's always, whatever kind of integral is appropriate to the problem at hand, it's always integral r squared dm. So please memorize that formula, integral r squared dm. It's always right for a moment of inertia. Okay. Integral r squared dm. Now I've just got to make sense out of it. Well, mass is density times area. Density, of course, given. So that's just a little bit of plugging in. Not much happened there. What can I say about R? Well, keep in mind I'm going around the x-axis, so here's our axis of rotation, and distance then from a generic point. So my generic formula for distance, let's see here, I'll use dark blue. Generic formula for distance there, you can see in the geometry of this picture, it's just y, right? Height above the x-axis is y. And so this r here is just y. Everybody okay? Yeah. Double integral, yada, yada, yada. Do make sure that you're good with doing integrals. Notice that some weird stuff does come up integration-wise. You do get a sine cubed. Make sure you remember all those little fancy little tricky little strategies for how to compute various single variable integrals. Stuff like this never goes away, especially for engineers. It's gonna, this kind of thing just keeps coming up. So make sure you're good with that kind of thing. Okay, is everybody okay? All right. We are done with chapter 5. We move on now to chapter 6. Let's pause and take stock. Let's talk about integrals that we've defined. Y'all came into this class having seen single variable integrals. Did a lot of things with them, but one concept of single variable integrals. We then defined double integrals. New concept, importantly different, two-dimensional domains, right? Pretty big difference in concept, but also strategically very similar. Whole is the sum of the parts. Chop it up, add it up. A lot of analogies, right? Nevertheless, different kind of an integral. Triple integrals was our next one. Three-dimensional domains, right? So again, fundamentally different concept, but also really analogous in a lot of ways. Now, then we've also done tons of computational methods, spherical coordinates, change of variables, stuff like that, symmetry, right? We've had various computational tools that we've talked about, but in terms of, fundamentally different kinds of integrals, we've got 3 so far, single, double, triple. Okay, we're about to add a 4th. All of the examples we've seen so far, the domains have been what I'm going to say, same dimension as the world that they live in. You do a triple integral, you have a 3-dimensional solid living in a 3-dimensional space. Here's the weird new scenario. Suppose your domain is a curve in the plane. And I say this is a really weird situation. So first of all, how could a domain be a curve? Well, keep in mind, if you want to do a whole is the sum of the parts, you could absolutely have a whole is the sum of the parts argument applied to a curve. Maybe this curve is a river, and you're counting fish in the river. And for environmental reasons, you know that there's more, fish per mile in the river at higher latitudes and fewer fish per mile at lower latitudes, and you know the shape of the river, but you want the total number of fish, but the fish per mile varies. And so how would you find the total number of fish? Well, you would break up the river into small little pieces, and you would say, all right, well, on that little piece, I know how many fish per mile, and I could multiply fish per mile times miles, right? And then I can add that up over the whole length of the river. So just, broad strokes, just strategically chop it up, add it up, totally makes sense on a curve in the plane. Now, again, I claim this is a brand new scenario. Single variable integrals don't address this. Double integrals don't address this. After all, my domain is intrinsically one-dimensional. There's no area on my curve. It's a curve. Length is the only notion of size that I can talk about on that curve. But it lives in a two-dimensional world. And we have never seen anything like this before. Double integrals, nope. Triple integrals, certainly not. Single variable integrals are on an interval, not on a curve. So we're in a new situation. We define a new kind of integral. Again, here's the formula. We already kind of talked through what this means. We're taking our curve, we're chopping it up into little pieces, and on each little piece, I can make an easy argument. Fish per unit length times length. Maybe I'm computing the mass of water in that river, and so mass per unit length of water in the river times length. Maybe the water is deeper in some parts of the river and shallower in other parts, whatever. But quantity per unit length times length always gives quantity. Everybody okay with that? Big picture strategically. Now, how to actually compute this, how to get answers, totally separate matter. We'll get to that in a minute. But just big picture strategy, this is just chop it up, add it up, applied to a geometrically new situation. Okay. Alrighty, let's talk notation. I hope this notation doesn't come as too big of a surprise. We're going to use an integral symbol to represent the summation limit thing, as we always do. We represent deltas with D's. Again, that's just notation, just like we've always used before. So I think the notation's pretty believable. Don't forget that the curve itself, the domain, the thing that you are chopping into little pieces, that has to be represented in your notation. As with double integrals and triple integrals, we make it a subscript. So the notation, I think, is pretty believable. And terminology, we call this a line integral. It's a little regrettable. If we could go back in time and just get everybody onto the same page, get them calling it a curve integral, I would totally do that if we had a time machine. But it's very much in the culture. This is called a line integral, and just, oh well. So just remember, the curve does not have to be a line. That's just terminology. What is a little bit mysterious at this point, and I'm going to have to ask you to just kind of, for the moment, just don't worry about it. Why we call this a scalar line integral? Short answer, there's going to be another kind of line integral that we're going to see pretty soon here. It's very different from this one. It's similar in some ways, but it's importantly different in other ways. One of the distinctions is that for this integral here, for example, you notice the differential is a scalar. It's length. It's a scalar concept, right? And the integrand, also a scalar. Now, you may be thinking to yourself, how could a differential be anything other than a scalar, for crying out loud? How could an integral... What are the other options? What else could it be? Again, be patient. We'll answer that question in a few minutes. Well, either in a few minutes or next week. But there is another option, and we're going to see that arise naturally. Okay. All right, so the term we're going to use, scalar line integral. All right. Now, let's go on to the next question. How do we compute these things? Hard question. Frankly, we had to get creative when we saw double integrals and triple integrals. We don't have a fundamental theorem of calculus for double integrals. Right? We had to get creative, and it turns out that, well, okay, you can do this thing called an iterated integral, and you can make the case that iterated integrals and double integrals will always give you the same value by way of a geometry argument, blah, blah, blah. It was a whole thing. Right? And we ended up coming up with a computational strategy. We're going to have a different computational strategy here. It's going to be kind of a ripoff of the idea of change of variables. And it goes like this. Here's my domain for a line integral, scalar line integral. And I'm going to just make the innocent observation that I don't like it. I don't like that domain. It's dimensionally awkward. It's a one-dimensional thing in a two-dimensional world. That's a problem. I don't know how to deal with that. What have we done in the past when we have a domain that we don't like? And we did this thing called change of variables. And the idea of change of variables is if you can find a way of viewing your domain that you don't like as an image, right? If you can view it as the output of a different domain that you hopefully like better, then you can do what's called a pullback. And the pullback allows you to take the undesirable integral over this orange undesirable domain, pull back, and turn it into an integral over this deliberately nicer domain. Okay? So that was the big picture strategy of change of variables, and that's exactly what we're going to do here. We're going to find a way to view our curve as being an image. Oh wait, we already have that. We already know, we have a pre-existing concept we've spent a bunch of time with for how to make a curve an image. It's parametrizing, right? So all we have to do here is just do the parameterizations that we already know how to do. And with that parameterization, we can do the pullback, and the result will be an integral on the t-axis, a to b, single variable integral, that we are really good at computing at this point. Everybody see the big picture? Okay. So, as usual, the big question is, what is the stretching factor? Let's talk stretching factors. Keep in mind the idea of a stretching factor is that a little piece of the t-axis and its image, in this case a little piece of our curve, those are not the same size. Right? When you have a function that pushes a domain forward, things get contorted and distorted and stretched, and all sorts of changes happen to them, right? So if I want to know what is the relationship between output size and input size here, that's what my stretching factor is going to be. So what is my relationship between output size, which is distance, and input size, which I'm going to think of as an amount of time. Not that you have to think of your parameter as being time, but it sure is handy. And in this case, I want to think of it as time. So what is the relationship between distance and time? Well, it's speed. Pre-existing physics concept we've all seen before. The relationship between distance and time, or said differently, distance per unit time, is speed, and so that is our stretching factor. We already had it, as it turns out. So, as it turns out, everything we needed to pull back off of a curve, the idea of a parameterization, the idea of speed, pre-existing concept, we already had it. We had everything we need, we just had to write it down. And here it is then. ds turns into speed times dt. The integral then goes from a to b on the t-axis. Don't forget to plug in that position is a function of time by your parameterization, and we're in business. We got a single variable integral. Off to the races. Plug and chug. Let's do some. Okay. Oh, I keep getting ahead of myself on this. I do want to talk about this handy fact here first. Before we get into an example, here's a concern that we could get upset about, conceivably. Well, this parameterization, what if I use one parameterization and you use a different parameterization? Are we going to get two different answers? Which is the right parameterization? What would we do if we had two different answers for two different parameterizations? This is a natural concern. By the way, the book spends a bunch of time worrying about this. This is among the topics that the book is worrying about more than we really need to. That's more sort of, mathematician formality that this course isn't really about. So I'm just going to cut to the punchline, and that is, doesn't matter. It's completely independent of which parameterization you pick. Use whichever parameterization you like. Doesn't matter. It's a wonderful answer to this concern. It's just not a problem. Okay. All right. And again, if you're curious, you can read the book's treatment. You're not responsible for it. Okay. So here we go. Real world example. Let's suppose I have a bent wire. And not only is it bent, but it also has a non-constant density. So for whatever scenario, I don't know what the scenario is that would make this happen, but the mass per unit length on the wire is more in some places and it's less in other places. So why we would have such a situation, whatever, let's not worry about it. Okay, so that said, what's the mass? Total mass of this weird irregular wire. Where's the center of mass? What's the moment of inertia around the x-axis, let's say? A bunch of questions we could ask about this wire. I'm going to answer all four of these questions all at the same time with four separate integrals, but they're all kind of similar to each other, as it turns out. So, let's first of all, let's get the big picture done. Mass, total is the sum of the parts. Chop it up, add it up, say it however you like. Y'all will recall, of course, that mass is density times size. And so there you go in this case. And here we go. We have ourselves a scalar line integral. Now, for the x-coordinate of the centroid, weighted average. The x-coordinate of the centroid is the weighted average of the x-coordinates. Right, old idea from last time. And so again, I get to argue about mass being density times size. And again, scalar line integral. Different scalar line integral, of course, than this one. But nevertheless, a different scalar line integral. Likewise, moment of inertia. Integral r squared dm. Always the same formula. Make sure to memorize that little expression, integral r squared dm. Here, scalar line integral r squared dm. And again, mass density times ds. Weighted average of the y-coordinates gives you the y-coordinate of the centroid. And again, mass is density times size. Okay, is everybody with me so far? All right, now, in order to proceed on this, I'm going to need to rewrite ds. Here's how we do it. We talked about this up here. ds is... Whoops, I missed. ds is this business right here. I'm going to need, therefore, to compute my stretching factor. My stretching factor is speed. Let's go ahead and get that done. Let's compute that speed. Okay, here we go. Well, there's our parameterization. Derivative gives me velocity. Magnitude gives me speed, which of course is my stretching factor, so we're in business. There's our stretching factor. Everybody okay? And that allows me to proceed here. So ds is stretching factor times dt. Notice the same exact thing happens in all of these integrals. It's the exact same stretching factor because I have the exact same parameterization because I'm talking about the exact same curve. So Of course, it's the exact same stretching factor. And then likewise down here, same deal. All of this is the same for the exact same reasons. All right. Okay. So let's see here. The last thing I'll point out is what do we do with, like, for example, the x and the y right here? Oh, I guess I should point out that was the that came from density here. We have density is x plus y, so I plug that in here. Density is x plus y. So what do I do with the x and the y? This is an easy thing to forget. A lot of students forget this. When you're trying to figure out how to plug in for x and y, don't forget that that's what the parameterization does. The parameterization literally gives you position x and y as the output values of that function. So in our case here, looking at our parameterization, that right there is x. And this right here is y. And so you can just plug that in. Everywhere you see an x, it's t for this curve, because we have that parameterization. Everywhere you see a y, t squared. So here we go. Let's see here. X is t. X is t. X is t. Let's see. X is t. You can see why I wanted to do these all at the same time. There's a lot of shared sort of aspects here. Likewise, y is t squared. Y is t squared. Y is t squared. Y is t squared. Y is t. There's a lot of them. You can see it's very efficient to do them sort of all together. And after it's all said and done, I have 4 separate single variable integrals to compute. And you just plug and chug to compute these. Is everybody with me? By the way, I recognize that these particular integrals would be super inconvenient to do, and this is just these are just an example to show you how these integrals develop. I'll make sure that integrals that you have to compute on the exam are all reasonable. Okay. All right. Here's a different example. Let's suppose that I have a property, and the property line is a circle, let's just say, right? And I want to build a fence, and I'm going to build a fence that sits on top of the property line, something kind of like this, right? But I'm going to do something weird with this fence for reasons that we could speculate about. I'm going to make it taller in some places and shorter in other places. Strange. It's going to look weird. But I might have a reasonable reason to want to do this. Like, for example, maybe I have a vegetable garden on one side of my plot of land. I want it to get a lot of sun. I don't want the fence casting shadows on my vegetable garden. Right? But on the other side of the plot, chicken coop, and I want the chickens to get more shade. So easy, hypothetical. Okay. So, how do we compute the area of this fence? If you have a constant height fence, it's an easy calculation. You just look at the length of fence, tape measure, right? Multiply by the height, boom, there's your area. But here the height varies. I have different height in some places versus others. So what we're going to have to do here, if you look at, here's a sort of an exploded drawing here. There's my property line. Here's the fence, like that. And on any given little piece, I can talk about the corresponding picket, right? And if I look at this little piece of the property line of size ds, I can compute the height of that picket based on the given function. And the product then, height times ds, is what gives me my area for that particular picket, right? And so that area is height times ds. What do you say? Oh yeah, question.
For this example, how, like, isn't the fence two-dimensional?
Oh yeah. The fence itself is kind of that's right. So that's why I'm talking about the area of the fence.
So I thought we were talking about like when there's like a mismatch.
Oh yeah. Oh, good. Okay, let's talk about that. So what we've got here is an integral. So here's the development of my integral here, right? And so this is an integral, but it's an integral that's happening over the property line, which is a curve. Right? So for each piece of curve down here, it's only for each piece of curve that I compute the area of the fence that's above that little piece of curve. So the domain here is a curve. Now, why am I computing an integral on this curve? The reason I'm computing an integral on this curve is because that integral is going to compute an area. Yeah, absolutely. But the domain itself is still just a curve. Does that make sense? Yeah, it's a great question. Yeah. Okay. So, we got an integral to compute here. Let's dive in. How do we compute line integrals? Well, we've got this formula back here. If you want to compute a line integral, compute the speed. The speed is your stretching factor. And basically, just don't forget to insert the speed and go ahead. Plug in, pull back, and off you go. So we're going to go ahead and compute this speed. Now notice, in this case, parameterization wasn't given. No parameterization given. Conveniently, I know how to parameterize. This one happens to be an easy one. Unit circle, easily parameterized with this old trick right here. Does everybody remember that one? Yeah. Okay. So there's my parameterization. We take the derivative, we take the magnitude. Lucky break, the stretching factor happens to be 1. Cool. So looking at our DS. DS is stretching factor, aka speed, aka 1 in this case. Stretching factor times dt. We're given in the statement of the question that height is that function of x and y. There is the remaining question: what in the world do I do with this x right here? Again, easy to forget. How to deal with that. X is the output, one of the output variables of my parameterization. Don't forget that means that it is given in the parameterization itself. X is just cosine t in this case because that's what the parameterization says. And so x becomes cosine t. And now we truly have a single variable integral and plug and chug. Everybody good? All right. Okay, let's see here. Now I'm going to start some thoughts that we're not going to get very far into, but I do want to plan a quick thought. I want to try to do the same sort of thing now. We're going to do an integral on a curve. Correction, we're going to chop it up, add it up in some sense. I hope this works out nicely. Right? I'm just going to proceed not knowing. But what I want to do is compute this quantity, work. Now hopefully y'all remember work from chapter 1, force dot displacement. And so here's the problem. That formula makes certain assumptions. This formula assumes that your force is constant across the entire displacement. It isn't always in the real world. Right? In the real world, you can have forces that vary wildly. So this formula doesn't work when you have a non-constant force. So we're going to have to figure out how to deal with that. Next thing we're going to have to deal with, and this is an ugly reality, you're not always going to displace by straight lines. But this formula assumes that you are going over a straight path. If you're going over a not straight path, well, that's reason number 2 that you cannot use that formula. Right? So, back in chapter 1, we were all proud of this formula and stuff because it was such an improvement over the really bad high school formula that treated force as scalars, for crying out loud, right? And treated displacement as a scalar. like the direction doesn't matter. It's just really naive, right? So this was an improvement over the high school formula, but it is still very narrow, and we need to generalize. The big idea is we're going to chop into little pieces. We're going to say, look, the total amount of work is the sum of how much work does it take to move along each little piece of the curve, and then we're going to add up over all those little pieces of curve. And the good news, on each little piece of curve, it's approximately straight. Not exactly, close enough. Round off errors go away in the limit. And the vector field is approximately constant because it's a little piece of curve. There's just not much movement there, and so the vector field just doesn't have much distance to change very much. So we're going to, on each little piece, be able to basically use this formula, and then we're just going to add up over the whole curve. But there's some sticky wickets that are going to arise. We'll deal with those next week. We'll call it a day here, drawing the line. I'm going to draw the line right here, and we'll pick up there on Monday. Y'all have a good one. Good luck on the test. See y'all Friday.